Okay, after introduction about the slicing, so you will get pieces, many pieces of silicon wafer. So from silicon wafer, we have the specific geometry, not only the disc shape, not a round disc shape. We will cutting something out from the disc to identify the direction, crystal orientation, or crystal direction. For example, for wafers with a diameter between 4 inch to 6 inch, we always have the primary fret. Primary fret, as I show you in the figure. Primary fret. Most of the wafer we use right now is a plane 100. 100 plane. And the primary fret has a direction along 110 direction. All this 100 or 110 index is what we call meter index. In crystallology graphic, this kind of, in the crystal structure, we use the meter index to identify the plane and the direction. So primary fret is necessary. Without the identify the primary fret, we doesn't know what the crystal orientation on this 100 plane, crystal plane. Sometimes the plane is the direction is important. It's important because we need to do the cutting from the silicon wafer into small chips. Right after fabrication, overall wafer will separate into small chips. For small chips, right now we use a small dicing saw to do the slicing for the small chips finally. But in the past, we use diamond knife. We use a diamond knife to scrape the surface, like cutting the glass. Like cutting the glass, because silicon is a very hard, brittle material. So you cannot use ordinary cutting method. You can use the method like cutting the glass. So you scrape the surface and then little bit excitation it will break automatically. Along his we call it the natural beverage plant. It will automatically break separate into two crystal planes. Very beautiful. So only the cutting scraping direction along 110 is possible for you to separate the chip from the original wafer. So we follow the tradition, the cutting. So we identify primary fret on the wafer, and all the direction or layout of our semiconductor device. We always align, do the alignment along the primary fret direction. So in that finally, this crystal, this single crystal crack will be divided into many like chips. So all these SY lines along with 110 direction. It's much easier for us to finish the final chips of our devices. So it's the old way for us to doing the assignment of the direction on the wafer. But for 8-inch and the 12-inch wafer, right now the size is too big, very big. So we abandon the way of primary fret. We only left a little place, we call it a notch. Only do a little bit machining, small part of the cut, we call it a notch. This notch is exactly with the tangent direction of the primary fret, the same. But you can say the area originally primary thread means. Because if we use the primary thread over here, if you have primary thread over here, we will sacrifice a lot of area. Because the area denotes money, right? More area can make more devices for you to sell. So we want to earn more money, so only left a little bit notch. Okay, the direction guidance. That's quite enough for us. So this brace is exactly the same as this brace. Exactly the same as this brace. So it's an alignment mark. It's an ornamental alignment mark. We must follow. Okay, so this is the slicing. After slicing, you know the surface roughness is no good. No good slicing. So surface roughness should be modified. So we need a lapping process. Lapping is something like the meter polish. Actually, like polish. So we need the polishing machine to do the lapping. Something like the grinding, very similar to grinding. So after grinding, and then we can reduce the surface roughness from micrometer down to maybe 0.1 micrometer. And then we keep doing the CMP, chemical mechanical planarization, or chemical mechanical polishing. Okay, down to about 5 to 10 nanometer average roughness, surface roughness. So whatever you apply a silicon wafer, you will find the surface is mirror-like, very shiny, very flat, without any defects, very beautiful. It's because it's after the lapping, after the CMP process. And CMP process will not only use here for you to prepare the wafer. CMP process will keep be used in our actual world semiconductor process. So in chance I will try to tell you the detail. And for the wafer, you can order 100, 111, or 110. 3 kinds of wafer you can order. But most of the wafer right now used is 100. And I show here. Most of the wafer are 100. And so very, very expensive, very, very cheap. If you order other kind of wafer, it is possible, but very expensive because nobody wants to use that. So if you order one batch, it means that they need to pour an ink cup for you. Pour the exactly ink cup for you. You should buy all of them. Otherwise, nobody wants to do the stock for you. You just buy. So the total price is huge. No way. So you can use the 111 or 110. So I show some wafer specification here. Specification. You can crystal orientation 110. When you order the prime crystal orientation here, it didn't mean the there's no error about orientation. No, you have always 1 degree deviation. 1 degree deviation. It's not exactly matched with the exact direction of the crystal orientation, crystal structure. So you have some deviation angle. Meter from 3. 3 number now very rare to find. So maybe it's 4, 6, 8, 12. very hard to find 5 inch, very hard to find. So the very standard size of the wafer you can order. Thickness from about 500 micron to about 800 micron. Impurity, 2 kinds of impurity, P-type or N-type. Right? It depends on the dopant. Depending on the dopant impurity inside. If you have P-type, P-type means you have the boron inside. If the N-type, it means you have phosphorus. You have phosphorus, graphite element inside. So it's a P-type or N-type you should order. Resistivity is trying to understand what is the conductance, right? Conductivity of your wafer. So we often have the value about 0.01 to 100, but usually better order the resistivity around 0.1 to 10. It's much easier to find. If you have the 100 or 0.01, it's very hard to find. Some of them are because if you order the very rare specification of the wafer, you get more money to buy them. Methodology, I will show you CZ or FZ. Right? 2 kinds of method, right? It's a dichotomy method. It is a 14-zone method. 14-zone method always match with the impurity or resistivity. If for 14-zone, you will see the resistivity is higher. So if you order resistivity, for example, 100 or 10, the methodology always FD. So you cannot show you a specification in a random way. You can say, oh, I have dichotomy method, I want 100 CM. Impossible to provide. Polish method, you can ask one single phase or double phase. You can only one phase or couple phase. It depends on your fabrication requirement. If you need to do 2 phase photolithography, you need 2 double phase polish. If only one side is necessary, only one side. Double phase is double price of the single phase. Okay, so this is the wafer preparation. We only finished the listing about the semiconductor. Right now we are keep talking about the detail about the semiconductor, thin film, growth, photolithography, and the etching. But so actually yesterday, today, and tomorrow we're supposed to complete all the semiconductor processing. So let's talk about one by one. Oxidation. Oxidation is the first step to silicon wafer. Oxidation, first step. When you buy the wafer, first step you need to do is oxidation. Try to oxidize the surface of the silicon wafer. The silicon wafer has a good quality of they can grow the oxide directly from itself. Now silicon dioxide is the silicon combined with oxygen in the air. Right? So if you put your wafer in the air for a period of time, you will naturally grow the oxide. We call it native oxide. Even at room temperature. Because the oxygen is very chemical reactive. So it's very easy to touch with your silicon surface and you oxidize. Do the oxidize even under the ambient temperature 35 degrees C. The native oxide is not very thick, maybe only several nanometers, only several nanometers, very, very thin. You can even ignore it. Or sometimes we don't want to ignore it because if you want to do very good device, you need to straight out remove the native oxide. Otherwise, because the quality of native oxide is very hard to control, so you have better remove it. But if you want to do the very good isolation or protection, for oxidation, oxide it has two functions. One is electrical isolation. Oxide is the main material of glass. Like glass plate, the majority material is oxide, silicon dioxide. So it's used for electrical isolation and HMX. Because what? We can use the glass as a container to hold in any kind of base and chemical, right? Acid, even strong acid. We use the glass container to hold it. So it means that it can prevent the attack of the acid, strong acid. So it's a good as an edge mask. So two functions for the oxide, electrical isolation and the edge mask. And also we have two kinds of oxide available for dealing with these two problems. If you want to have an electrical isolation for MOS transistor, we need a high quality oxide, we call it the dry oxide or gate oxide. If you want to have the edge mask always need very thick oxide, maybe as thick about 1 micron. 1 micron thick oxide is very thick. Don't order say, oh, I want to 5 micron thick oxide. Impossible. The maximum thermal oxide for you to grow, maybe the maximum, maybe I believe, maybe only 1.5 micron. You cannot order very, very thick oxide. So edge mask should be thick, so we use the wet oxide or film oxide. So these two kinds of oxide have different kinds of growth. Not only the different temperature, we use a different reactant. For dry oxide, we use oxygen, pure oxygen, to grow the dry oxide or gate oxide. So it's a high quality oxide. We use oxide gas to grow. But if you only need the wet oxide or pure oxide, we use water vapor. We provide the water vapor into a high temperature furnace. We can grow the wet oxide or silver oxide with a very high speed. So about 1 micron maybe only need you to grow about 3 to 4 hours. You can have 1 micron thick water oxide. For the dry oxide, gate oxide, we don't need to very thick. MOS transistor, MOS, metal oxide semiconductor, MOS transistor, all is oxide. This oxide maybe as thick as several tens or 100 nanometer is quite enough. Maybe 0.05, 0.1 micron thick is quite enough for us. So you don't need to perform the oxidation, dry oxidation too long. There is the two functions and the two kinds of oxide. In the first set of semiconductor process I have mentioned, 1 micron thick oxide will sacrifice 0.4 micron thick silicon substrate because oxide comes from the element of silicon in silicon dioxide is come from the silicon wafer. So more thicker in growth about the silicon dioxide, more thickness about the surface silicon will be sacrificed. So it is show here 1 versus 0.44. This ratio is a chemical stoichiometric relationship. Number 6, nonlinear growth rate versus time. It means that when you grow the oxide, you cannot say maybe 1 minute can grow 100 nanometer and so on. the growth depth versus time is not a linear relationship. At the first moment it's a linear, and gradually into square root rule. Time tend to take the square root of time. So we have become nonlinear. Nonlinear means you spend a lot of time waiting for growing thicker oxide. So it's also the reason say it is impossible. It is impossible for us to grow very thick oxide. The reason is we need to transport the silicon atom from the bottom to the top. It's very difficult. You need to go. You need a diffusion process, mass transport process. So it's not easy to do that. So basically, silicon oxide is a nonlinear growth rate, nonlinear growth. 7, orientation dependent growth rate means that if you have different wafers like 111, 100, 110, different growth rate. The total, the surface, the silicon surface atom density is different for different orientation. But right now, most of the people use 100, so no problem with consideration. Second is less than 1.5. I mentioned that. This is the furnace, high temperature furnace. It is a very old machine. It's a horizontal type. You can see all our wafer we are vertical. We have vertical installation on the boat, on the quartz boat. We use the quartz. Quartz is the crystallized silicon dioxide quartz boat, and holding the wafer vertically and then same into the high temperature furnace gradually. And the temperature inside is more than 1,000 degrees C. So you should be careful about the surface tension, about if you not properly place the wafer inside, it's very easy to be broken. The silicon wafer is very easy to be broken, or even have the plastic deformation, permanent deformation. If your wafer distorted, more fret is useless. So the potential of that is a furnace. It's a batch process. We can put 50 pieces, 25 pieces or 50 pieces, the wafer together, send into the furnace, grow simultaneously at the same time. So ordinarily we buy one box of wafer, give you 25 pieces of wafer. So you can put one box of wafer or 2 boxes of wafer at the same time. So oxidation process is a very cheap way. So we have ever evaluated you do one process of oxidation maybe only cost you $5,000. Divided for each piece, maybe each piece only cost you about $100. So it's very easy. 200 BTU per piece. It's not costly. And at the growth, we need to identify the thickness. Thickness, how you can know how thick the oxide is. So 2 ways to measure. One way is destructive method, another is non-destructive method. Destructive method is we partially etch by BOE, buffer oxide etch, BOE. BOE is dilute hydrofluoric acid. The only one acid can attack oxide or glass is HF solution. HF solution called the hydrofluoric acid. It's a very dangerous one. It's similar to DI water. It's similar to water. Transparent, no smell. But very dangerous. If you touch it with your hand, your hand will got permanent damage. Permanent damage. So you should be very, very careful about the BOE. BOE is buffer, but the original one is HF. HF is very dangerous. So we use the dilute. Dilute HF BOE maybe only 6%. 6 to 10%, so it's not so strong, but even very, very dangerous. So this kind of agent solution can attack oxide, can remove oxide. So we remove partially oxide and measured by service provider or other step. This is the machine can measure. We use the stylus to do the scanning, so it can measure the contour of your surface. So if there is the oxide and there is no oxide, it will show the high difference on the monitor, and you can measure the difference of thickness of your silicon dioxide. But this is a destructive way. It means that we do some etching on the wafer, so this wafer cannot be used again. You should remove everything, do the cleaning once again, otherwise it's no function. If you want to keep the function of your wafer, you had better use the non-destructive way. NDT or NDN is a non-destructive way. It means that we use the optical way, optical measurement to detect the thickness. So you can use by ellipsometer or nanospec. These two kinds of machine to measure the thickness of oxide. Ellipsometer need a laser to help you to measure. They use some polar optics to help us to identify the thickness, or even more the refractive index of the quality of the oxide group. So it's a very important measurement tool, ellipsometer. Nanospec is an much easier machine. You can only measure the roughly thickness by the white line, general white line. So you can use this machine to measure the thickness. Or even more, some expert they can judge the thickness of the wafer with the oxide or not by its color. Pure silicon is a gray color, like the silver, gray color, like the platinum or silver is a gray color, silver color. But if you have oxide grow above, maybe its color will change from silver to originally if you have 1,000 micron, 1,000 angstrom or 0.1 micron. The color is about deep purple color. If 3,000 angstrom or 0.3 micron, 0.3 micron, the color probably like the light purple color. If you have your thickness up to 1 micron, the color will change to light green color. So we have ever measured and identified and comparison the surface color. So we can just have a look about your wafer and we can identify maybe your thickness is about this range. So it's by experience. Or you can do the color comparison by the color chart. Different color, the reason, right? It is due to the diffraction, the principle of diffraction. So there is some, they have some interference, right? Between the Because oxide is transparent. It's naturally no color, transparent. But due to we have one line touch the surface to refract, one line penetrate the oxide and refract back. So there is some lag about these two times the beam line. So they give you some interference effect. So you can only some specific light you can see. Only some frequency the line can be visible. So the reason why I have different color. But if you have your thickness, such oxide thickness more than 1 micron, for example 1.5, transparent, will become transparent once again. So your wafer will turn back to gray color. Will become gray color. So because very thick is something like a glass, very similar to the glass. So no interference happen. So for our so we have experience to judge. If you have measure is similar, it's reliable. But if you cannot measure, you can try to experience to do the measurement. The thickness measurement. So oxidation is a fundamental step, very easy step for us to do. And the first step for you to do, you must do the oxidation at first. Of course, right now you can order wafer with oxide directly. You can order, you will go to the shop and order, okay, I want to one box for silicon wafer. 1 micron thick oxide, grade oxide, they will provide you, but extra charge on the oxidation process. So each wafer maybe from $500 maybe increase to $2,000, for example. More expensive, but easier for you to apply. Second process I want to talk about is diffusion. Because diffusion uses a similar machine as the oxidation. The machine very similar to this, very similar to the oxidation furnace, but some difference. Oxidation is only feeding the gas with oxygen or water vapor. But if you want to do the diffusion means that I want to diffuse good number 3 or good number 5 elements into my silicon subsurface to become a P-type area or N-type area. You need to add some doped gas inside under the high temperature furnace. So they use the similar apparatus furnace to do the thermal diffusion. And this kind of thermal diffusion is exactly a solid diffusion. Solid is a diffusion phenomenon that happens in the solid. Dopant is solid, silicon is solid. These two kinds of solid material want to fuse together. Impossible to happen in 25 degrees C, but possible for the temperature larger than 550 degrees C. So it's a high temperature process. For high temperature process, we have the mass transfer phenomena. Mass will go from the high concentration to low concentration area with a mass transfer phenomena or diffusion phenomena. Well, here is a Fick's law to describe this kind of phenomena. Actually, it's a diffusion equation. Diffusion, partial differential equation. It is a concentration, partial T, the concentration partial S, is the second time. And this is a diffusion coefficient. Become very large at a high temperature. So it's a Fick's law, mass transfer. So maximum concentration on the surface. So in the high temperature furnace, we put wafer inside, and then we we release the dopant particle we are attached, right? Attach on the surface, and then gradually try to, from the surface, try to diffuse into inside. It's something like a stain, right? Something like a stain. Some color dye on your surface and gradually deepen and deepen, make it deepen and deepen. So it's a diffusion phenomenon from the maximum concentration on the surface and diffuse inside. So you have some thickness for influence area with the dopant. And if you don't want to have this area have dopant, please mask it by oxide or nitride. Even that if no oxide or nitride protection, all the vapor will diffuse with the dopant. But if you only several spots or several windows should be dopant with need dopant, you just open some window and do the diffusion. So before that, you need to do the photolithography. You need to do the photolithography to open the window and let the dopant go into through the window. We additionally separate diffusion into two steps. First step is the pre-deposition. Second step is post-drying. What is the pre-deposition diffusion? Pre-deposition is exactly diffusion. With ordinary diffusion we mentioned about. You put vapor inside, right, some open window, so diffused dopant will automatically goes in. Right, is the diffusion. It's the ordinary diffusion called the pre-diffusion or pre-deposition. And his model about the diffusion can be explained by the complementary error function distribution. We have no time to talk too much about this. If you have interest, you please refer to my teaching material. Okay, after the pre-deposition, during the pre-deposition or pre-diffusion, dopant gas or dopant solid particle always releasing. Okay, but after you release it for a long time, you will find saturate. Even if you block the time of diffusion, no more dopant will go into the surface. Impossible because too much. It's something like the traffic jam. Very similar to the traffic jam, right? A lot of cars going to highway, nobody can move anymore. So we need to wait, right? We should waiting for the car to drive away. Otherwise, traffic jam is over there. Similar, if pre-deposition counter a saturation phenomena, you should wait. But how to wait? It means you must stop. You must stop the dopant release. It's something like for the freeway, right? We have the traffic jam blocking over there. You should block the entrance of the freeway, not allow other cars to enter into the freeway, and waiting for all the cars on the freeway to go away, right? So in need time, this is what we call the post-drying. Post-drying. Under such situation, we stop releasing the dopant. We only keep the temperature over there. So the surface dopant will keep diffusion to the underneath area. Will keep going down to a deeper area. So you call it the drying. This process is very similar to the thermal treatment of a meal. But very similar to some material process, we call it anneal. Anneal is something that we have some damage in our structure. So we put in a high temperature furnace, holding up there, just feed into some nitrogen gas inside, prevent them about the oxidation and holding for a long time. So the microstructure can try to restore, right? They can fix and restore to their original state. Something like that is what we call a neon. But here, very similar, but a little bit different. We will not order them to do the neon. We let them to diffuse more into our wafer. So we call it the dry beam. Dry inside, dry more inside. What's dry beam? And the model, the mathematical model is about Gaussian distribution. Gaussian distribution. It's a normal distribution, actually. Normal distribution. Okay, so we try to pre-deposition and then stop for a while to do the dry beam, and then go to review one more, and then open, release the loading once again, and stop loading for a long time. So repeat several ways. You can try to adjust the conductivity of your silicon surface. Okay, but overall, the thermal diffusion process is the very old process, maybe from 1960 or even earlier. It's a very old process. So diffusion has his problem. His problem is what we call the over-diffusion. Over-diffusion, because diffusion is a natural phenomenon, the transport. So if there is a high concentration, we'll go to the low concentration. So very hard to prevent. Even we have some masking to stop, right? To stop. But when you grow inside, you will go to the lateral diffusion. Not only this way, but also they can do this way. But for our idea diffusion is only located over here, right? And we hope to this way. Directly downward. Directly downward, but impossible. You will diffuse in the lateral direction. So we call it the over diffusion. Over-diffusion is bad for small device. For example, if our open window is 1 micron, finally you will find the surrounding 3 micron area of wafers. It's not good. It's not good because it's very easier. If there's another diffusion here, right, then you can see. If there's another diffusion here, it's very easy to cross-talk, right? Cross-talk is lateral, the device side. If it's a short circuit, you have a short circuit problem, right? So we try to prevent this phenomenon in the sub-micron device, a smaller device. But impossible, right? Because diffusion is a natural phenomenon. You cannot prevent it. You cannot prevent it. So diffusion is no use for the sub-micron device or nano device. Impossible. So we change to use the ion implantation method. Ion implantation. Okay, I talk about ion implantation at the first. ion intervention X that it mean that try to make up for the weakness of diffusion. Because diffusion cannot do it in the soft micro device, they will have the lateral or over diffusion phenomena. Diffusion. And what is the ion impartation? Ion impartation means, okay, we turn our dopant into the configuration of ion. For example, boron. We use boron ion. We can charge, so we can accelerate in the electrical field. So we can accelerate like a bullet, like a missile. Touch your single surface, penetrate, or even deepen. But in the vertical manner, there were no lateral component, only vertical component. So it's very good for you to do the very vertical diffusion, vertical doping. Vertical doping. So we call it the ion implant. Ion implant. So the maximum concentration will not on the surface, but on the underground, under surface. Because you touch the surface, it can depend. Finally stuck. So the maximum dopant area is underneath the surface. So we don't use the pre-deposition. We use ion implant to do the doping directly. But you need dry beam little bit. Dry beam don't need to do it a long time. We use the post dry beam try to remedy the